orthogonal cutting. I want to refresh you guys' memory about this common terminology. The red-handed cutting tool, left-handed cutting tool from other three different views. Characteristics of machining, and we talk about this from turning and to this sawing. We talk about turning, and we already talked about drilling, and then today we are going to talk about milling. So the parts produced by machining processes. So here is the machining processes. This is A, is a B, this slot, this is you can mill A. And so this is this one is a forming accurate. So here it is forming also. So here is a pier and all machine is gear. This is not the basic machining, so it's very complicated. And then we talk about milling. Milling is more versatile and also more useful. Milling, more complicated. So milling, what is the difference? Look at this picture. You can see the difference. What's the difference between the milling and turning? Well, turning, the tool remains stationary, right? The workpiece is spinning. But on the contrary, for milling, the tool is rotating, is spinning, but the workpiece remains stationary. You see that, right? So the milling we can produce very, very complicated features, very, very small features, different complex features. So that's the reason milling is more important. So here, this is a cutter with milling cutter, and so this is a workpiece. This guy, I'm sorry, the workpiece is not remain stationary. It is translating, but the milling tool is spinning. And for in the lathe, in the turning, the tool remains stationary. Here is must have this is the relative motion between the workpiece and the tool. So this is a slab milling operation. You just want to have a flat surface. So here is my final surface. Here is my original surface. But this is my workpiece. I want to have final surface and to remove all these things. So B is a slab milling operation. I show you depth of card for this one. This is the depth of card. The depth of card D, and how for one carding, and how much you want to remove. This is the D, depth of card. And the feeder rate F. So this is depth of card is in this direction. And feeder rate, and this is a feed per tooth. If one tooth rotating, and this is my feeder per tooth, so this is F, right? So this is F. For one tooth, and it goes in this direction, this F. So this is called feeder per tooth. So chip depth of card, TC, and here is a chip depth of card of TC here, chip depth of card, and workpiece speed V. So here's the depth of card D, and feeder per tooth, and also TC here, chip depth of card in this direction. Be careful. And we have two depth card. One is our normal depth card. Another one is a T depth card. And what is T? So here, schematic illustration of cutter travel distance. And so this is the travel distance. Okay, this is the D. And so here is the capital D, the outer diameter. So this D is the depth of card, and so this is the cutting speed. This cutting speed, this guy is rotating, and this guy is translating. So we have these two guys have this relative motion. So we can cut this part just above this dotted line off. So this one will be the final surface. Here, common machining processes. This is speed turning. We talk about it. And this is cutting off. So this is slab milling. This is cutter slab milling. So this guy is rotating and this guy is translating. And here is the end milling. End milling. And we can get very, very complex features. Right? So here, I just show you how we can get this one. But we can get very, very small slots. Any kind of complex shapes, the small slots. So that's the reason the milling is more important than turning, more versatile than turning. And then we talk about, see, you can see this is slab milling. So this is end milling. See, end milling. Another milling is the face milling. And what's the face milling? And face milling, so suppose this is my work piece. This is my original work piece. This is my insert. My insert, suppose my tool holder is very, very huge. On the periphery, I have multiple inserts. Inserts means the tools, the cutting tools, milling tools. So this guy, okay, just say this. This is my, I suppose, this is my the tool holder. So this is 4 corners. And we have this is 4 inserts. So this guy, so this is my work piece, and this is rotating, right? It's rotating, and we'll cut this one layer off. So this is called face milling, as the name suggests. So from this corner, my tool is rotating this way, and finally all these things will be called face milling. So here, look at here. So this is my initial condition. So I'm going through in this direction. The work piece is moving in this direction. So I want to cut all these things off. Just the material to the left of this one. This work piece. And so this is machine series. One rotation, one rotation. This is the vehicle. Right? So here is the tool holder. Here's the tool holder. This is different inserts. For different inserts, we have this is the axle rig angle. Whenever you see rig angle, that means it's for the rig face, rig angle and axle rig. Why this axle rig? This is along this is axle axis. So this is here. This is end relief, also called axle relief. Here is end edge cutting edge angle. Here is end cutting edge angle. So this is radial rig in this direction. This is axle, and here is a radial. This is a radial rig, and also this radial relief. Are you okay with these two filters? Okay. Why I call it axle rig? Because I use this line, the central line, as a reference, and to measure this axle rig. For here, I use this radial line, this one, and this one, and this angle. Use this line and this rig face. This one is a radial rig. So that I have 2 rig angles because this is a 3D, right? This is a 3D. And 3D I have two rig angles. It depends on which perspective you are looking at. This is the tool. So cutting mechanics. So here, so this is insert. So these are undeformed chip thickness, And so here is the depth of card. And so here is a feed per tooth, F. What this guy, a feed per tooth. The effect of lead angle, the lead angle for this one is a lead angle. This is a lead angle, okay? For this one, lead angle equals 0. On the undeformed chip thickness in face milling, I know that as the lead angle increases, so this is increasing, the undeformed chip thickness decreases. That's the thickness of the chip. So you can see this one and this one. The decreases, but the length of contact from here to here increases. So know that the insert must be sufficiently large and to accommodate the increase in contact length. So contact length means from here to here, the tool shape contact. So here, full shape contact is from here to here. Right, so this is this picture. So we have undeformed chip thickness, capsule card, and feeder protrudes. So here, this one, relative position of the cutter is a cutter, and the insert as it first engages the O piece in this meaning. So first one is this is a cutter, okay? This is my cutter. B, insert position as the entry and the exit near the endo card. Entry when it comes here. When this guy engages with one piece. As entry and exit, this is as exit of the insert. Showing desirable or positive or negative angle. So this is an undesirable zero angle position. So zero angle is back, okay? So in all figures, the cutter spindle is perpendicular onto the page. The cutting spindle is understandable. Just assume. So this is my spindle. This location visual. And the main operation here. This is a spindle milling, and you can mill these two slots simultaneously. The spindle milling. The B is the forming. Right? The forming. So first you need to have this is a tool. This is a customized tool. First, the forming milling. And this is slot milling. The slot mill slot. And you can use this one, or you just use end milling to mill the slots. This one is a splitting operation. Just cut this into two pieces. Cut through into two pieces. And here are the cutting speed and based on different piece materials. The milling machines you have, I think you are familiar with these milling machines. Downstairs in the machine shop we have. So here is a horizontal. This is the work table is horizontal, and the spindle is vertical. Column and knee type milling machine. So this one is a vertical spindle. It's a vertical spindle. This spindle is here. This spindle is horizontal. This spindle is a vertical. These are two machines. These are T slots, and you just fasten this is low piece on the table. So this is a milling. And then we talk about the broaching. The broaching. So here are we have different shapes on these slots, the shapes, and we can broaching it. These are typical parts finished by internal broaching, right? So it is internal broaching. The B is a part finished by a surface broaching. Okay, surface, approach the surface. The highway lines indicate the broaching surface. The highway lines. See, the highway lines, the broaching surface. So C is a vertical broaching machine, just the broaching. Have you guys ever used a broaching machine? You just pull it. Pull it, just cut something off. If you use the machine, it needs to provide a big enough force. So this is broaching. Okay? So here's a cutting action of the broach showing various features. So this is a terminology for broaching. So we can see the teeth, okay? We have many teeth, several teeth here. And these are teeth steps. See? Right angle. You can see we still have big angle here. Also, we have clearance angle. See? Clearance angle, we have length. And from here to here, the same location on the neighboring teeth, we call the pitch. So this is the terminology for teeth. What do we have here? We see usually the different the teeth, and they just cut a new slot, a new layer. Is a pull on a new layer. So here is a typical. This is internal broaching tool. Very awesome, right? You tool it. You can shoot my demo machine, you tool it. Store. Next time, next one is a store. Store is, have you guys used store to cut either wood items or this metal, the store. Store is very similar to the broaching, but this is using the poly-off. This is a very plate. We have plates there. So here is a tool face and tool back. We have rig angle. This is a rig angle. We have clearance angle. You can see rig angle, clearance angle is very similar for the two angles for the orthogonal cutting. This is the bullet depth, and this width, and this back edge. So here is a high-speed steel teeth welded on the steel blade. So high speed because high speed steel, they can be the hardness is very high. Also at high temperature, the hardness does not decrease substantially. So here is this one is a carbide insert brazed on the base on the blade teeth. So this is just in order to increase the hardness. The gear manufacturing is a very complex one, and we will in the machine design class, and we will learn the gears. So gears, so here is a gear manufacturing. A is the schematic illustration of gear generation with the pinion-shaped gear cutter, and the pinion. You know pinion, right? So two gears. If we have two gears, the bigger gear will be still called gear, but the smaller gear we call it pinion. You understand that, right? You know this? If two gears and they are matching each other, bigger gear we still call gear, and smaller gear is called a pinion. Right down. So this is a cutter. So this is a cutter, and so this is the we call this a gear blank. Gear blank means the workpiece we are going to use for gear to generate the gear on it. So this is a gear blank. So this is cutter. The red one is cutter. So here another one, B is the schematic gear generation in a gear shaper using a pinion-shaped cutter, gear shaper. And so this guy goes down, up and down to get this is the slots. That's the profile of the shape. The C is the gear generation with a rack shaped cutter. This is a rack shaped cutter. This rack shaped cutter is going this way and to get this profile. The last one, the D is 3 views of gear cutting with the hob. This hob is so this is a machine, hobbing machine for gears. So this one is very expensive. So this is typically the 4 different the gear cutting. This is the method. Machining centers. Machining centers with so here this one is a horizontal spindle machine center equipped with automatic tool changer. Right? So automatic tool changer. And tool magazines in such machine can store as many as 200 cutting tools, and each with its own holder. So this is the tool storage, tools, cutters, a tool interchange arm, you can change it, and spindle, horizontal spindle, this one is horizontal spindle, and spindle carrier, and so this is pellets, right? This pellets, and this is the bed. So this one is the numerical CNC machine, the turning center, and we have this in our audio hall. Note that the machine has 2 spindle slides and 3 parallel heads for this one, okay? And our machine is kind of different from this one. I'm making the machine tool very flexible in this compatibility. This is a CNC machine. So then we talk about reconfigurable machines. So reconfigurable, as the name suggests, and we can just change some the models. So here is an illustration of reconfigurable modular machining center, and based on your needs, you can just reconfigure it. Capable of accommodating workpiece of different shapes and sizes and requiring different machining operations on their various series. So here is the bed unit, the base unit, arm unit, and for the linear motion, rotational motion, arm unit, and rotational motion, magazine units, different tools. It's a functional units, and you can just put them together, right, based on your needs. So here are the different components of reconfigurable machining center. So this is this kind of different. And based on each one is a model, you put them together. Any questions so far? A lot of facts. Well,
what was the thing you mentioned? There was like in something called like a pinion. It was like 2 slides ago or something.
yeah. So if we have 2 gears, if these 2 gears are matching each other, so this is gear, bigger gear is still called gear, and so this is smaller gear called pinion. Right? This is was a pinion. Question? The question we call chatter, vibration. So when we do this machining, our assumption is that our machine is stiff enough. And stiff enough means that the vibration of it when cutting is almost negligible. But actually, it is not the case. Right? So this one, chatter and vibration is a very, very important research topic. So here you can see if the tool, either tool or workpiece, neither one is vibrating, but these 2 guys still engaging each other. And so we will have the chatter marks. Chatter marks. The right of the corner, center of the photograph on the surface of the turning machine. This is the chatter mark. So this is a signal for the grain cast iron, damping capacity. Grain cast iron is an epoxy granite composite material. So this is for the damping capacity. The vertical scale is the magnitude of vibration, and the horizontal scale is the time. So here is a damping capacity. This one is much better than this one. Right? So the next one, damping of vibration as a function of number of components on the lathe. The joists dissipate energy, thus the greater the number of joists, the higher the damping. If the damping is high, you can just vibration can be reduced very quickly, but the stiffness is bad. So here's a bed only. So here is a complete machine. So this is the increasing damping. Machining economics. So this one, the qualitative plot shows the cost per piece. For this one, be the time per piece in machining. So cutting speed, if you increase the cutting speed, so this is the cost per piece. Increase the cutting speed, the total cost will go this way. Why? Because so this is the machining cost will be decreasing, but the tool cost will be increasing. Why? Because the cutting speed will shorten the tool life substantially. The tool change cost, because your tool will be worn out very, very quickly, so you need to more frequently to change the tool. So tool change cost will be increasing. So as a result, finally, so this is tool cost, this is per body. And at this point, at this cutting speed, the cost per piece is the minimum. Right? And for here is the cutting speed.